Hello students, now begins our adventure into phase changes. We will also learn what a warming curve is. At the conclusion of the video, you should have become re-familiar with the names of all phase changes and with confidence conclude if that phase change is exothermic or endothermic. You will understand and be able to interpret a warming or a cooling curve and be able to perform warming or cooling curve calculations shooting for 90% accuracy. So let's begin by reminding ourselves of our different phase changes, just of our three main phases of matter. All right, if we have the lowest energy associated state, and then the highest on the right, or the lowest entropy, and then of course we're increasing in entropy. So let's move from low energy to high. Solid to liquid, of course, is melting. And liquid to gas. Now, you may have thought, oh, boiling or evaporation, those are actually two specific types of vaporization, or we'll say vaporizing. All right, let's go in the reverse direction. Gas to liquid, that would be condensing, or the gas would be undergoing condensation. Liquid to solid, of course, is freezing. However, we can actually go right from solid to gas. That's also going from low kinetic energy to highest, and that is subliming or sublimation. And then gas to solid, that is depositing or deposition. In the direction of left to right. So solid to liquid, liquid to gas, or solid to gas. In the direction where those arrows are pointing, those are all endothermic. They require the input of energy, often in the form of heat, hence therm, of course. In the reverse direction, those, of course, are exothermic. We need to know all of these names. Now, to actually go from solid to liquid, again, that's going to require the input of energy. And we actually give that a special term. We call that the heat of fusion. Now, in chemistry, if we're undergoing a phase change or a chemical process and we're not changing the pressure, then we often can rename heat enthalpy. That's just a fancy kind of word, but pretty much synonymous with heat. And enthalpy has the symbol of H. Remember, entropy, disorder, was capital S. So if we see that, this is talked a lot more about in second year chemistry. Often, these heats of fusion are molar heats of fusion, and that is simply the energy required to melt 1 mole of substance once it's at the temperature for melting. Sometimes it can be given per grams, but then it wouldn't be the molar heat of fusion, of course. Remember, heat, a form of energy, well, that will be in joules, possibly kilojoules. So very common units for molar heat of fusion will be joule per mole. Now, remember that whenever heat is being absorbed or being added, it has a positive sign. And to melt, it's endothermic. So these will be positive. Now, we also can relate and talk about the molar heat of vaporization. And that would be the energy, of course, in joules, required to vaporize. And required, it's endothermic to vaporize 1 mole, if it's molar heat of vaporization, 1 mole of substance. and that will be positive joule per mole as well. If it is given differently, joule per gram or something like that, then of course it wouldn't be called molar. Now, you bright students, we'll come back to this. How about that? I think it'll make more sense for predictive if we come back. So this will be kind of a cliffhanger to see where I was going to go next. All right. I always find it interesting that students often definitely have things that they know about water. So for example, I think most commonly we know the boiling point of water is 100 degrees Celsius and the freezing point is 0. But we're often stumped about the condensation point or the melting point. But why? So let's experimentally investigate this. Let's imagine, ladies and gentlemen, that we had a ring stand with an iron ring and a beaker of solid water. So imagine we filled it with pure water, added a temperature probe, and then set this in the freezer overnight. And so we're starting with all solid water. And then we apply a heat source. And what we're going to do is monitor how temperature changes as we apply heat, starting with the solid state. Now, I know that the freezing point of water is 0. So I'm going to start at a temperature, why don't we say at negative 5 degrees Celsius. And what we're going to do is we're going to monitor, maybe take the temperature every 30 seconds and then graph this. And what this graph will come up creating for us is what we call the warming curve. Now, why do we call it the warming curve? Because we are monitoring temperature change as we are applying heat. And so we would understand that that would go to warm, increase the temperature, increase the kinetic energy of the substance. All right. If we're going to start at negative 5 degrees Celsius, we're going to talk about water because we're nice and familiar with that. Well, depending upon the intensity of the heat, the sample size of our water, that will dictate how long it will take for the temperature to change. So I'm just going to be generic and let's say, let's go ahead and take our temperature in minutes. So maybe every 30 seconds, so half minute. So probably what's going to happen is what we would predict, that we going to begin solid and then our temperature will increase. I mean, temperature is directly related to kinetic energy. Temperature is a measure of the average kinetic energy. So as we're adding heat, we should increase temperature. Well, our temperature is going to go up, but then it's going to flatline. It all of a sudden stops changing, but we haven't turned off our Bunsen burner. But what we start to see is liquid form. And then if we continue to apply heat, but keep taking our temperature, eventually all the solid is converted to liquid, and then we begin to increase in temperature again. And we keep going, and then all of a sudden our temperature stops changing. But what we'll observe is the beginning of vapor, and then boiling. And eventually all our liquid will be gone, and if we keep our thermometer there, the vapor will continue to increase in temperature. So we started with solid. Here we had solid and liquid, then just liquid, and then we started to get bubbles, and then just gas. All right, so warming curve. We are transitioning between solid to liquid to gaseous state, a physical change. Well, don't you know for water, this is 0, and this would be at 100. Pure water at sea level. Okay, so what is going on here? This is where we're getting our phase change. So if we're warming, here's where we just started to see liquid form. But do you note there's no change in temperature? There is no change in temperature. Remember that delta means change in. There is no change in temperature during a phase change. But why? We kept our heat added. Well, ladies and gentlemen, what that heat is going to do is actually accomplish the phase change for us. Now, remember, temperature is a measure of the average kinetic energy. Here, our temperature is not changing. So where is that heat going? It is going to the phase change. This can be called latent heat. This heat is not changing the kinetic energy. It's changing the potential energy. All right. Once we have gotten all liquid, well, then the heat can go to what it wants to do, make the molecules move faster and faster and faster. So their average energy will keep creeping up, creeping up, creeping up, creeping up, creeping up, until we're at what would be the boiling point. Then liquid will be converted to gas and there'll be no change in temperature. Again, latent heat. All that energy is going to overcome the particle attraction, not changing kinetic energy, but changing potential energy. And then once we have all the phase change complete, all the particle attraction overcome, then we can go to changing the kinetic energy of the substance. Okay, so here, by gosh, where we first start to see liquid, well, that, I'm going to mark that here, well, that would be our melting point. And then here, well, that would be our boiling point. Because whenever we go from solid to liquid to gas, we're going to melt and then we're going to vaporize. Well, what if we started with gas? What if we removed heat? Well, the first place we would start to see gas going to liquid would be here. So in the reverse direction, it would just be, boop, we'd have to flip over this, and we call it the cooling curve then. We're removing heat. So then gas first showing liquid, that would be the condensation point. Then we'd have all liquid, and then we'd remove heat, decreasing in temperature, less and less kinetic energy. And then here, where we first have liquid going to solid, that would be the freezing point. Okay, so what is the condensation point of water? So many of us think, well, just under the boiling point. No, it is the same temperature as the boiling point. So the condensation point of water is also 100. We know the freezing point is 0. Well, we think somehow the melting is at a temperature higher than the freezing point. No, it's the identical temperature. So how can you be freezing or melting at the same time? It depends on the direction of energy input. So we'll go back to where I left you in suspense. So if we are going in the endothermic direction, it's the molar heat of fusion and the molar heat of vaporization. Well, what would be the molar heat of freezing? Well, that would be just the negative of the molar heat of vaporization. Oh, fusion, sorry, the molar heat of fusion. Remember, ladies and gentlemen, that heat is negative when it's being released. So if we would take the value that we have to input to melt and put it at, if we take the amount of energy we have to invest to melt, but then reverse the sign, it'll be the energy that's released or that we have to remove to be able to freeze. So To vaporize, we have to invest energy. That will be a positive sign. Well, the negative molar heat of vaporization would be the molar heat of condensing. So your phase change happens at the same temperature. Temperature does not change during a phase change. The heat is going to change the potential energy to be able to accomplish the phase change. And we just have to know which is the endothermic and which is the exothermic direction to be able to predict what phase change is going on at that temperature. Okay, ladies and gentlemen, the next video will show us how to tackle those warming curve calculations.